everyone. I'm Wauford from SMART Photonics. That's an indium phosphide foundry in Europe, particularly in the Netherlands. And I'm going to talk about, what's beyond indium phosphide. I mean, what's just beyond silicon photonics. All right, so silicon photonics has done a nice job of demonstrating how photonics integration has a lot of value, but had a number of limitations, which we'll talk about. And we can take indium phosphide integration, can take it much further to really create much more groundbreaking, game-changing products for the data center. So a little introduction of SMART Photonics. We are an indium phosphide foundry in Europe, particularly in the Netherlands, really focused on the next generation of integrated photonics, both actives and passives. That's one of the things that makes us different. Most indium phosphide fabs are just doing lasers. We do much more than that. We are an independent and open foundry, as we don't make products. We have technology. We enable people to create products with our unique technology. We focus on really creating the fabless ecosystem for indium phosphide, similar to what TSMC did for the CMOS environment. So you don't need to have a fab to create very sophisticated indium phosphide PICs. We help you do that. And we focus on high volume, low cost manufacturing in the indium phosphide integrated photonics. So if we look at the data center, I'm sure this is this very common looking diagram here. You have three different architectures, right? You have the scale up inside a rack where you maybe have 1,000 GPUs, very low latency, right? You have the scale out network. So AI clusters are much more efficient when they get bigger. The more GPUs you can put in an AI cluster, the more efficient and is the AI capabilities, right? So people moved a few years ago to scale out networks. I want to now have GPUs in different racks inside the same data center. You see now people building data centers that can have like 100,000 GPUs in the data center, and you can create that all into one very big AI cluster. And now the next architecture is I want bigger than 100,000. So 100,000 is what you can get in a single data center. If you want to go beyond that to 1 million, for example, GPUs in an AI cluster. You get longer latency in that case, but you get many more GPUs involved. So you have these three different architectures, but you all have similar sort of limitations, right? To scaling the data center and to scaling the performance of GPUs, right? Your limitations in a data center is access to power, right? And how much power every device uses. Its density, it's particularly faceplate real estate, say on the switches and the GPUs. The number of fibers in a data center is also a constrained commodity, right? And when you look at GPU performance, it's really about what's the bandwidth between GPUs, right? What's the latency? And any failure mode can have a huge impact on the performance of an AI cluster. A single failure, right, can cause a couple of hours worth of that whole AI cluster basically just spending time resyncing, right? And therefore not making money for the customers. So the way to make these, to work on eliminating these issues or reducing these limitations, right? We think is higher speeds, right? The next generation of AI pluggables, right? And more integration. So here's a chart that shows basically that links the speed of the lane speeds and the typical data center pluggables. 100 gig lanes, which is what you use for your 400 gig and some of the 800 gig modules, right? Is widely deployed out there. That's all in a modulator speed, right? It is 30 gigahertz or so, right? We now see this year, we've seen a lot of, and late last year, a lot of 200 gig per lane products come out. That's where you have your 4 by 200 for 800 gig modules, 8 by 200 gig for 1.6 gig modules, right? There you need the 60 to 70 gigahertz modulator, right? That's where silicon photonics is now running out of gas. You can't get past 67 gigahertz, 60 or 70 gigahertz with a silicon photonics modulator. You need to go to a new technology. So that's a change that we're going to have in our products to go to 400 gig per lane, right? To double the bandwidth, right? There you need like 110 or above gigahertz in that modulator. The two technologies that most people talk about, right, are thin film lithium niobate, which has a nice modulator, right, but is very hard to integrate, right, and it's still relatively young in the volume manufacturing cycle. The alternative, the other one is indium phosphide, where you also can get 110 gigahertz up to even 200 gigahertz modulators, right? You can do tons of integrations. You have many photonic functions that can be integrated together, right? And you have 35 years of high volume manufacturing experience. Here's the SMART Photonics 110 gigahertz modulator based on indium phosphide. You can see there in the upper left corner, you have a Mach-Cylinder modulator with a phase shifter, on-chip termination, all integrated in a single device. The graph on the right shows some performance, shows our performance. The orange line there is actually our real tested with the Keysight 67 gigahertz based test set. Right, you can see the nice performance we have there. We also have very good simulations. You can see the blue line there is a simulation of that same device. Goes out to 100 gigahertz for the 3 dB optical bandwidth. Right, and the red line on top is a similar device, slightly different configuration, slightly better impedance match. You see that goes out to 120 gigahertz for the 3 dB bandwidth. And like I said, this modulator can be integrated. On the lower right there, you see a DFB integrated with this 100 gigahertz modulator to create basically a small 400 gig per lane EML. As I said, indium phosphide and particularly SMART Photonics provides a huge range of functionality that you can integrate photonically. If you look at thin film lithium niobate, it's basically just a modulator technology, just like lithium niobate was before, right? Silicon photonics, a bit better. You can do modulators, limited to 70 gigahertz or so, right? You can do passives. It actually does a pretty nice job with passives. And then you can dope silicon with germanium, and you get some low-speed photodiodes. Right. But then you look at indium phosphide, and I would say most indium phosphide fabs are just doing lasers. But at SMART Photonics, we do lasers, tunable lasers, SOAs for amplification, right? Photodiodes up to 110 gigahertz. We do modulators up to 110 gigahertz and beyond. And we also focus on having very good passives in indium phosphide that allows you to do, as it shows here, a chip that can generate light, right? Can amplify light, can modulate light, can detect light, and can, with passes, move it around and shape it. So like, again, we don't make products, but we do try to inspire people to make products. So here's a concept that we've done. On the far left there, you see basically the functions you need for any FR4 transmit side. You have 8 lasers. In this case, we have the 4 CWDM4 wavelengths, right? Each feeding 4 100 gigahertz modulators. That's 400 gigs per lane, right? And then passes doing a 2 sets of passes doing a 4 by 1 mux. And then you see in the center there an actual design of a chip that we designed, right? I don't have a laser pointer, but the lasers are on top there. The red lines you see are the modulators. They feed into, you can look at the little blue lines there. They mux into 2 outputs on that chip, right? And that's the heart, right, of the photonics that you need for a 3.2 FR module for the transmit side. And that's what we see people going to in the scale out market for next generation. When you look at the scale up, right? So inside the data center, people are talking about going to CPO. In a CPO solution, you need a light source, right? And so typically those are EOS modules, right? Here's an architecture on again, you look at the left there, there's a block diagram. 8 DWDM lasers, right? All broadcasted with a passive star coupler to 8 outputs. Each of those outputs has a high power SOA, right? So you get 64 different wavelengths on 8 ports. So 8 wavelengths for each of the 8 ports, right? That allows you to have a lot of very power. The laser is actually a low power. SOAs boost the power, right? You get 64 different wavelengths on 8 ports, right? So you don't need 64 ports for your connector. You only need 8 ports, right? And as you see there in the middle, there's a chip that does that. Every laser there has also has an optical monitor. They go to the star coupler and they broadcast on these 8 ports, and each port has a nice big amplifier there to boost the power. And also we have PICs. You can create PICs for coherent, right? So this is actually a PIC with a tunable laser, full C-band tunable laser, right? With IQ modulator, right? And an SOA, right? And then on the right there, you can see an actual on our test set in our office, right? And the integrated SOA, particularly for coherent, is very valuable, right? Because with coherent, you always need amplification. If you don't have it in the chip, which you can't do with anybody else, you have to have it outside, typically an ETFA. Adding an ETFA to a pluggable module basically doubles your cost, right? And that does not even include the assembly cost. So just to summarize, right, we talked about the 3 different architectures in the data center. Each one of those, we can create a very valuable, very interesting, very cost-effective PIC to handle most of the photonic functions, right? We can, with that, right, with our 110 gigahertz modulator, you can double the speed, get 400 gig per lane to enable the 3.2 data center pluggables, or 1.6 ZR plus coherence, right? That's going to lower your power per bit because you're increasing how much data you're pushing through it. Twice the bandwidth in the same pluggable module. Twice the bandwidth on the fiber for much more bit utilization, right? And then with the photonic integration, right, you can eliminate, you can have three times less attaches, fiber attaches. Fiber attaches are really basically very expensive to manufacture, right? They're also a very weak point for reliability. And thirdly, they're a place where you lose power, right? So as a result of that, you get much better reliability by eliminating those failure points. You get much less power in the system because you're not wasting power at these fiber connections, right? And because of the integration, you get much smaller footprint, 3 times much smaller footprint than compared to thin film lithium niobate, which is a very big chip, right? And you get wafer scale economics, right? So you can create this chip and then you can just put millions out. We can just fab millions of these devices on our fab. Just sort of wrap up. So I talked about, integration on the transmit side, right? You can integrate the receivers as well. So you get one PIC that does all the photonics for transmit and receive, right? And the other thing you get with indium phosphide is also very good, very high speed drivers and TIAs, right? And the future would be to bring that functionality into the photonic chip. So you're doing electric and optics in the same chip. Thank you. Any questions? Yes.
So first, when you say integrated, you mean it all goes on the same die, or is it chiplets in the same package?
Yes. So good question. I mean, it's monolithically integrated, so it's all single die. So we go back here, right? All these were single dies. Go back to my favorite one. All right. So it's all single die, right? Singles in all in the initial steps. So no hybrid or heterogeneous integration here.
Okay, that's good to hear. And I have another question about your supply. Where do you get your blank wafers from? How much of the indium phosphide supply depends on China?
Yes. So good question. I know people are concerned about the supply. So we have long-term relationships and with both European and Japanese suppliers. So nothing comes directly from China, right? We also use iron doped iron doped wafers instead of sulfur doped wafers. So there's a really big shortage right now of sulfur doped wafers. It's much easier to get the iron doped wafers, and then we have long contracts with people, multi-year contracts to get indium phosphide.
Okay, good to hear. Thanks.
And there's ways that we are also working to start harvesting and recycling the indium phosphide as well. A lot of indium phosphide is getting grinded off, right? So, right. Yes.
Just have a question. So the wafer fab size and number of die per wafer, could you comment on that?
So today we have a 4-inch fab for indium phosphide with 5,000 wafers a year. We are currently building a 6-inch fab, which is state of the art for indium phosphide, with 20,000 wafers per year capabilities, right? All right, and then dies per wafer, it's tricky because wafers, a DFB, is less than a millimeter and less than a quarter millimeter wide, right? This chip is basically 2.5 by 3.5. All right. The next one was more like 20, more 4 by 4.5. So it all, it depends on that, and how clever you are on how you create it, right? So one of the arts is really about how to pack that stuff really closely together. And one of the things we enable, right, in our photonic solution here for indium phosphide is very tight bin radiuses. So that you can, a lot of the things I showed were straight, but you can bend them around. For example, back. This EML on the bottom here is all in a straight line, but you actually can bend the contacts. You can take the phase, phase shifter. You can put it in line. You put the laser close to the modulator, so you can actually create this about 1/3 of the size as shown here.
Very good. Just second question. Are these standardized die or are they typically done custom, and what level of rel qual have you completed?
What was your first question?
Are they standard die that you're offering or are they more built?
So we offer a PDK, right, with 50 different building blocks, all right, including DFB lasers, the modulators. So I would like to say we do the hard part, right, which is knowing how to make lasers, right, how to make modulators. But then the value the customers bring is how do I want to put that together? How do I want to create a circuit for a particular application, right? So then that's custom. So the building blocks are standard, right? The circuits are custom, and our customers own those designs that they do of the circuits, right? And how well they pack them together, they own that too, right? So then every circuit is custom, right? But once you create that, we can create 10,000, 1 million, 5 million, 100 million of them.
Very good. Thank you.
Thank you. And one way we do that, by the way, is that we are the only indium phosphide foundry that has a DOV scanner, so for lithography. This is the same technology they use in very high volume CMOS technology. So we can do 1,000 wafers in a day of doing the lithography. All right. So whereas if you're doing, especially like a 6-inch wafer, you're doing that with what most people use in a foundry, which is E-beam, that's 18 hours. So the difference between, 5 minutes and 18 hours. Any other questions? Okay. Thank you, everyone. I'll be here. We can have more questions if you have them.